objects. Procedural languages could cope. But these days, we need to look beyond isolated programs and think instead about systems. What's the difference?
The biggest distinction probably between a program and a system is that I run the program, it does its job, and then it's done. When I run a system, I get it started and it has to keep on running. And that means that I expect to maintain that system over a long period of time.
A system that we all expect to keep on running is the global telecom network. It's perhaps the most elaborate hardware and software system that humans have created. To manage this staggering complexity, the industry is increasingly coming to rely on objects.
So today I wanted to share with you some of the experiences and insights that we've gained as a provider of object-oriented technology to the telecom industry. One of the neat uses of object-oriented technology is to develop a surveillance and control application. What we're seeing is a national map of a telecommunications infrastructure. We can see a number of different alarms with different severities, and if we choose to go into this Atlanta alert, so here we see the city map of Atlanta, and we're able to see that this regional office here is actually where the physical fault is located. Alternately, we can take another view at this and scope down even further to see what actual equipment is involved in that failure. I've asked the system to tell me which technicians have the skill set to replace that failed component and where are they located. So we see that Ken is off to the left of the failed area. John Skyberg is probably the closest rep to it. Joe Peterson's probably too far out of the city. And then Pam Marciano maybe has more than 4 tickets outstanding. I can say, John, scoot down to that regional office at 55 North Central Street, because object-oriented technology allows me to very quickly assemble a very complex view of that information. And I can actually walk through the central office, down to the bay, down to the rack, indeed the frame, and actually the card level, and say, John, look straight ahead at eye level. It's the 3rd card from the left. John merely has to pull that out, slap in the new one, and I can remotely turn that card back on to service. That, ladies and gentlemen, is the power of objects. If you look at a modern-day telecom network, it is very dynamic. It is very, very complex. It is very difficult for any one person in a telephone company to tell you how does the whole network come together. Software has to be able to deal with that network complexity, and that's why we're seeing the real rush into objects. Customers are much more sophisticated nowadays. They want customized services. They want discounted pricing. And how are you going to respond to that? Object-oriented gives us a way to look and decompose that complexity, capture it in an object notation.
There's no doubt about the success of objects now, but it's taken a surprisingly long time to happen. In the early 1970s, a far-sighted project was underway at the Xerox Palo Alto Research Center, or PARC for short, to find out what an office without paper and Xerox copiers might look like.
The task? To create and shape the office of tomorrow. To study the true needs of the office. Design not just machines, but a system.
The 1970s at Xerox PARC was a time of great invention, working with people who didn't know that things were hard. They just went after their dreams. And of course, that was very stimulating. I know that at one point my mother was appalled that I said I was going to work, because she never viewed what I was doing as work, because I was always happy to get up and happy to go there.
Xerox PARC was the most fun I've had, I think, in a sustained period. Well, it was just full of really smart, really capable people.
One of the really incredible things was that since we were building our own hardware and our own software, everything was under one roof.
And we had a pretty much open charter to try and invent the future.
Here's the painting program. This is something I designed in the summer of 1972.
Alan Kay was about to invent the future, personal computers running object-oriented systems. The idea for objects was to come from earlier work in the 1960s.
Ivan Sutherland's Sketchpad would have to be called object-oriented today, although he didn't think of it quite that way. He was trying to model things in the world's first real graphic system. But you can see that if you have an idea like a rivet that it might be useful to have a notion of a master rivet and then be able to create many instances of them, because it's rare that you just want one of something.
A major influence on Alan Kay was the programming language Simula, developed by Kristen Nygaard and Ole Johan Dahl.
I think starting around 63 or 64 in Norway, Nygaard and Dahl wanted to simulate really large, complex things like oil refineries. And again, they were led to this notion that there's not just one valve, but there are going to be many, and not just one pipe, there are going to be many pipes.
Simula allowed complex systems like a North Sea oil terminal to be simulated in software. Programmers could manipulate components which combined information and behavior in single units of software. This concept for system building from components that keep information and behavior together was already familiar to Alan Kay.
The fact that I had been a molecular biologist in the past became very important, because the idea I had was that what these systems were trying to be like is something like what cells do in living organisms. When you have just the simplest principle in all of its different possibilities, to be able to get an almost unbounded amount of complex structure. So I had an epiphany on, it was November 11th, 1966, you never forget. That was when I realized that this was one of the great things trying to happen that anybody had ever done with computers, because when you apply it back to computers, you realize right away that the dumbest thing you could ever do with something powerful like a computer is to divide it up into almost static things like data structures and procedures. That was just an accident of history, because mathematicians fooled around with computers in the 50s, and they didn't know any better. But the really smart thing to do with computers was to divide it up into little software computers.
It was these little software computers that Alan called objects. At Xerox, it was the perfect environment to develop the idea with like-minded colleagues.
Powerful rules of thumb is that if you make something easy enough for kids to use and then turn around and use it with adults, it'll actually work pretty well.
By the time of its release in the early 1980s, Smalltalk had become a complete programming environment. Smalltalk 80 pioneered the commercial use of overlapping windows, mouse interaction, and the combination of text with graphics, the hallmarks of modern personal computing. It seemed objects were ready to cause a revolution, but the industry was slow to take them up. At Xerox, programmers created their own customized hardware to run object software. The outside world was unwilling or unable to do the same.
The main reason it's taken so long for people to become immersed in objects is because the original object systems were large, which required a powerful, therefore an expensive computer to run. So at Xerox Palo Alto Research Center, around the world in computer science laboratories, only the elite had enough money to afford the machines that could run the large object browsing and object development software.
Fortunately for the object-oriented world, the hardware advances really astounded most folks, and so it wasn't long before Smalltalk really was a viable alternative in industrial strength programming.
But in the meantime, another route to object ideas had been developed, surprisingly via the programming language C, which doesn't include objects. C is a simpler, cruder language that runs quickly on a wide variety of computers.
C became a very widespread language, but it lacked the power of objects. It's a procedural language. It makes you think about solving problems in one way, but it doesn't have the robustness of objects. So at ATT Bell Laboratories, a researcher added objects to C. They called it C++, an operator in the language C. This was far better, but big. And as it turned out, not simple.
Even though C++ is cumbersome and can be difficult to use, it was widely adopted by programmers. Why was it that C++ was preferred to Smalltalk?
People are inherently resistant to change, And they didn't feel they were making as big a change by moving to C++ than if they moved to Smalltalk, which was a whole different model of computing.
Although C++ created many converts to object design, it does have a major drawback.
An error was made in the construction of C++. It was possible to do the same thing many different ways. That yields instability in large programming systems. One programmer will choose one pathway to solve a problem, another programmer chooses another pathway, and it now is time to maintain the program by reading their code, and they can't understand what the others did. Too complicated. So at the very beginning, this overlaying of objects on C, while at the beginning a powerful new idea, in the result yielded a large and complicated and therefore fundamentally unstable system. Java replaces that.
Java is the object programming language that sounds like it doesn't have anything to do with computing. Developed at Sun Microsystems, it's taken the internet world by storm. But Java wasn't originally designed for the internet, and it wasn't called Java at the start either.
Java was originally designed by James Gosling, and James actually started with C++ as an implementation language for consumer devices like televisions and radios and toasters, and he found that C++ was hard to deal with, so he created a new language that at the time was called Oak.
That stuck for a while, but when it came time to actually release it to the world, I felt that we needed a name that would capture people's imaginations and make them kind of stop and go, whoa, that doesn't really sound like a programming language. So the one thing I didn't want to do was call it something like D++, you know?
We had several meetings in which we sort of brainstormed, and you know, after hours and hours, some guy said, well, we might as well call it Java, looking at this coffee cup full of Java coffee.
It's been surprising to me the effect and the impact that the name has had. When I came in, we were focused on the set-top box market, the interactive television market, because that was a very hot market at that time. So the idea was there would be fiber to every curb, you know, running up into every household in the world.
And the idea is that you would have a set-top box that sits on your television, and it downloads objects, which are, you know, perhaps an object to let you choose which program you want to record on your VCR that night, or so forth.
It became apparent within a pretty short period of time that that world was not going to happen anytime soon, because the infrastructure, the network infrastructure, was not going to exist. The internet was just starting to take off in the end of 1993. So we basically refocused Java to this new low bandwidth internet-based world and designed a browser called Hot Java that would basically enable little tiny programs to be delivered along with a web page. And this was a huge breakthrough.
And then once Java got really popular, we all got up and left and formed Marimba.
At Marimba, they've got Java hard at work building internet-based applications. For instance, they've produced a toolkit for creating user interfaces. Java is also being used to broadcast software across the internet with the aptly named Castanet application.
What Castanet aims to solve is the software distribution problem, to really enable people to write a substantial application in Java and to actually be able to distribute it to a user's machine. And in order to do that, what Castanet does is a very intelligent caching mechanism. It downloads a program once, and from then on, whenever the program changes, it only downloads differences to the program rather than the entire program.
So if you have software for buying office supplies, it can be automatically updated to include furniture, so that as you progress through the company, you can order the appropriate chair for your position. Meanwhile, kids on the internet have had the latest coloring book broadcast to them. Although Java is becoming many people's first introduction to object-oriented computing, it owes much to its predecessors like Smalltalk.
Smalltalk was a very important inspiration for Java. It was one of the most important ones.
With Smalltalk, they took the object-oriented metaphor almost to the extreme, which creates a very clean language, very, very simple implementation. but it's not necessarily always the most efficient one, and also it's also not always the most convenient one. And in Java, in sort of instead of aiming for purity, we aim for convenience, and that's kind of a sort of compromise you need to make sometimes.
The object ideas in programming languages are important, but programming is only part of what's involved in building software systems.
Programming is an important activity that's part of the larger activity of working on a team to meet customer requirements to deliver a software system.
Okay.
Adele Goldberg and her colleagues have created a Smalltalk programming environment that helps people to learn how to work in teams to build systems. This system is a virtual world inhabited by multiple users on the network.
David, create me a taco stand.
Sure.
The team are cooperating across the network by using objects to create and change this world. Here, the system is altered by varying the number of customers waiting for fast food at a taco stand.
There they go.
The system, which simulates the city, can be made as complex as the users want to model real-life complexity. Just like a real city, this virtual one can have sharks which feed on the citizens. But there's a serious point here too. Using object-oriented design makes it easier to maintain a system that has to keep on running and keep on changing.
We have enough experience now to know when we build a system for business, it does last 20, 30 years. It isn't the same thing we built the first day. It evolves. We will be able to know where to make change. Can we keep it local, or is it going to spread through lots of parts? And the reason we'll be able to do that is that we'll understand how the parts fit together, because the relationships are made explicit. The relationships are objects just like the parts are objects.
Alan Kay and Ted Keller continue their passion for working with Smalltalk. The plan is still to develop systems for kids, a project that has taken them to work for Disney, a company with a significant presence on the internet. Now that objects are finally in the mainstream of computing, how does Ted feel about the long wait for wider acceptance?
We joked around that it takes 10 years for a programming language to become accepted by the community. And so we figured rather than work really hard and be frustrated during those 10 years, we would just take them off and come back later and enjoy the success.
Object-oriented programming is at last a great commercial success. It's not been easy, but it's been worth the wait. It's no coincidence that wider recognition of object technology has come with the rise of the internet. If the future of computing is the network, then the future of the network is objects.
This is the adventure we're embarked on, and we're just at the beginning. The global reach of the network has only been evident in the last few years. Exponential growth in the speed of the network and the breadth of the reach of the network in the next few years will reach far beyond the current 1 or 2% of the world population that use computers. Today, the supposition that what we write affects only a few computers is wrong. What we're developing today is a new world that allows thousands of millions of devices to communicate with each other. To build the machinery for that, the independent small programs that must interact in this new environment, that's all based on object technology.
A computer-based
I didn't realize you were...
Tell me what Java is, really. I mean,
Well, Java is actually a small island in the Indian Ocean.
Welcome to the world of object computing.